We'll start with module 4, land use land cover classification. Start with script 1A, where we'll implement a basic supervised classification workflow. The goal today is you will select a city that you want to work on, create a Sentinel to composite, and then we'll collect training data. So we'll take the input image and we will collect training data. How do we get training data? Historically, you had to go to the field. If you want to collect data on what does this pixel represent, you didn't have imagery that was high resolution enough to know from the pixel itself that what is it. So you'll have to go to the ground and say, I'm with my GPS receiver, I am in a boat, I'm in the middle of a lake, so this coordinate is water. Or you can say I'm standing in the middle of a road, so this pixel is urban. And you come back, you upload the data, and then that's what you use to determine your field data. Nowadays, satellite imagery with 10-meter resolution is clear enough that most classes can be seen from the image itself. So you can see, oh, this is the water, this is vegetation. So you can use your image itself to drop points and label points as training data. And that's how most of the training data is generated. Humans looking at images and labeling the data, saying, I see that this is a water body, I see this is the road, and so on. So we'll do the same. You will take your city, look at your image, and drop points representing different classes. Once you have the training data, you will train a classifier. We'll pick a classifier. We'll start with random forest. I'll show you how to just change it to a different classifier. So we'll use random forest, train the model based on the training data you collected. Typically, you don't need as much training data for a small city, 4 classes, 10 points per class will do the job. If you're working in a larger area, maybe 100 points per class is good enough. And you train a classifier and saying, I have this, few hundred label points, build me a model based on how should I classify the rest of the pixels. And then you go and run that model on the rest of the pixels. Classify all the image, you will see the classified image. You then look at it visually. If you're happy with it, great, but you also need to do some quantitative assessment. And there are different techniques that's used in machine learning for accuracy assessment. You typically reserve some training data, which you already labeled, and check the answer of the model against that. So if you have 100 points, which you didn't use for training, you can say, tell me what you think of this 100 points. And you compare the answer of the model versus the true answers that you labeled, and you can determine how good the model is. If you're happy with the accuracy, you can stop, or you can tune the parameters of your classifier, change the number of trees, change other parameters that you need. Test it. If the accuracy improves, if the visual appearance improves, it's great. If you're still not happy with it, and you say my model consistently mistakes roads for water, then you go and pick some more training points for both the classes. So I'll show you some more examples of that this where you're making a mistake is actually road, it's not water. So keep doing this. This is an iterative process. Once you're done and say, I'm happy with it, you do some post-processing, typically clean up the salt, pepper, noise, apply some smoothing, and then you're done with your classification. And the whole process from creating the input image to post-processing can be done in Earth Engine, and we'll show you how to do that. Here we are using Sentinel-2 level 2 data. We're looking at a city boundary. So this is a shapefile that I uploaded. This is the official city boundary for the city of Bangalore. And we create a median composite for 2019, clip it, and display that. And so this is what we have done so far. This is our image. I want to turn this into 4 classes. So let's see what classes we want. So we want to classify the image into 4 classes. We want it to classify into urban or built. Then we want bare, so where there's it's a bare ground. Then we want water and vegetation. We've chosen this class because most urban areas can be classified into either of at least one of these 4 classes. Also, they're easy to spot from your satellite image. If there was a class that you cannot determine through satellite image, then you have to go to the field. Imagine I had a class, crops, or maybe say wheat or soybean. Like I cannot see if the field is growing soybean or wheat, but I have to go to the field and collect the data. So if you're doing crop classification, you have to go to the field and collect data. For classes such as this, you can sit at your computer and collect the data. For kind of any classification algorithm to work, it works better with numbers instead of text. So we'll assign this a value of 0, class 1, class 2, and class 3. It's just that we'll say, take this image, assign the value 0 to the pixel if it's urban, assign 1 if it's bad, and so on. So we now want to collect training data. So the way you do this, you use the drawing tools that are provided to you here in the code editor. Let's start collecting data for urban class. So you zoom into a place in your image where there is some built-up area. Here we're defining urban as any built-up surface. So roads, bridges, buildings, etc. Whatever is a built surface, we'll use that to determine that it's an urban area. So we do the point here, and we click somewhere where there's a built-up area. You can see this one. So all the buildings here. Make sure when you are dropping the point, you are seeing the Sentinel-2 imagery that you want to classify. Do not drop points on the high-res imagery or the map below, because that map and the high-res imagery might be from a different date, not the date that you're trying to classify. So look at this and say, oh, this definitely looks like an urban pixel. Drop a point here. How do we identify that this point is urban? So we need to assign some property to it. If you drop a point, it just becomes a geometry, just a simple lat long. We want to assign some metadata to it, saying that this one is actually an urban. So we go to the settings button. So when you have this geometry imports, you can click the settings and change the type from geometry to a feature collection. Why feature collection? Because we can then store multiple points and assign some properties to it. So we can identify that this point is actually urban. We can also change the name of this import to urban and then click property. We'll create a property called land cover. So this is just the name of the column that identifies the class, and we'll put value 0 for urban. You can also change the color and click OK. So this is important. Make sure you click property and assign this value land cover. In our code, we are using all small cases. It could be anything, but just the way our code is set up, we'll use small land cover and the value 0 for urban. And now we can select this one and just drop points. We can drop some points on road and say this is also urban. You go to different parts of your image and drop the points. Make sure to give enough diverse examples. Don't just say, oh, I'm done, I've dropped 100 points here, because the materials for the buildings might be different in this part of the city versus the part of the city. So make sure you go to different parts of the city, show different examples, different surfaces if you can find. Mainly roads are important to classify because roads and water can get confused. So you drop points, and maybe 10 points per class for a city should be good enough. So we do this urban, and now we say we want to collect the next class, which is bad. So we come here, create a new layer. Same thing, we go to settings, change the name to be bad, change the type to be feature collection, property to be land cover, the value to be 1. We are using 1 as a class name, class number for bad areas. Change the color, and then drop some points over the bad region. If your city or the region that you chose to classify does not have any bad regions, you can skip this class altogether. There are many cities, Tokyo being one example, where it's hard to find a single barren pixel within the city limits. So if you live in an area like this, you can skip that class and do the next one. Same thing, we do the same thing for water. Land cover 2, and then drop points on water. When you're doing this kind of classification, try to always pick the pure pixels. So if you have a water that is covered in algae, do not select that, because that might be interpreted as vegetation. So try to select water which is pure, or at least not covered by other surfaces. So we drop some points, and you do the same for the vegetation class as well. So what you'll have is something like this. So you can see I have a script where I've already collected this training samples. Note that they are all distributed throughout the region. of interest. They're not concentrated in one part. And we have about roughly 10 points per class here, and all our feature collections. So this becomes our labeled data. So let's start our supervised learning process. We need to now create training data. So first, we say I will, instead of working with 4 different feature collections, we'll merge all of them together. So we'll create a new variable called GCPs. GCP stands for ground control points. This is the historic term used for training data for remote sensing, because we have to go to ground and collect the data. So we use GCPs because many of you might be familiar with the term. We'll just say take the urban one, merge the GCPs from where collection, merge from. Merge for vegetation. And now we have a single feature collection that contains all our data. So far, all we have is the lat long and a property saying that this is the land cover 0, this one is land cover 2, and so on, right? So we've just taken those points, labeled them, and that becomes our control points. For our training data, if you go back to the slides here, for any supervised machine learning algorithm, we need this table. We have only this column, right? We just have this column. We just have the class numbers. We don't have the reflectances from the image bands. To train a model to classify the image, we need to actually extract the reflectance values. So we have this composite image. Let's say print a composite image. This has got 12 bands, and we have reflectances of all 12 bands. Let's extract the reflectance at each point. So to do this, we can say overlay the GCPs on the composite and extract the pixel values. And this becomes our training data. So we can say composite dot sample regions. So this is a function that allows you to sample the pixel values from your geometries. Control space to autocomplete. Let's fill the parameter. What's a collection? GCPs. Properties. If our feature collection had some additional columns, we can discard them because this will be used for our training data. We only need the labels. In our case, we only have one property called land cover, which will be used as label. So we retain that. Scale, resolution, 10 meters. You can skip the other parts. Let's print the training data and see what happened. Remember, we had this 33 points. All we had was this labels. When we sample our composite image, we now have extra properties that are extracted from those 12 image bands. Let's look at each point, and you can see this is what each point looks like. It has got the band values extracted at that location from all those 12 bands, and we have the land cover. So now this becomes our table where we say, this is our input, predict that this set of input becomes 0. That's the job of the machine learning algorithm. That given this set of 12 values, you need to figure out the algorithm that will predict that this would be class 0. And similarly, you have other things. You can see this pattern of values look different. Build a model that it predicts to. So now we have the table similar to this, where we can send this to any machine learning algorithm. It'll learn from it and build the model. There's a question on the properties has to be a list. Let's look at the documentation from the sample regions function. It says properties has to be a list, the list of properties to copy from each input feature. So yeah, it has to be a list, even if it's just one property. Next, we have our training data. We'll train a classifier. Let's look at what classifiers are available in Earth Engine. You can look under e.classifier. You have libsvm. This is your SVM classifier. You have CART, which is a single decision tree algorithm. We have KNN, we have name base, we have random forest. This is what we're going to use. And we have some other classes. There's also a gradient tree boost. This also has been shown to work quite well. So recently, some people have had good success with this algorithm. Again, it's a one-line change in your code. So pick any, and then you can adjust them later on. So let's use our classifier. We'll also use smile random forest classifier. The smile here refers to a machine learning library called Smile, which is what is this algorithms are based on. It's a Java library that this algorithm uses. So if you are curious saying that I used random forest in Earth Engine, I used random forest in R, there are some differences. Why? Well, you can go and look up the Smile machine learning library. So SMILE stands for Statistical Machine Intelligence and Learning Engine. It's an open source library. You can look at the implementation. If you're curious about different parameters, here we have the parameters here. They're documented here, but you can say, what is the bag fraction? And how do I adjust that? You can look up the documentation for the SMILE library because it just uses that to do the machine learning. Yeah. There are so many parameters. We can tune them later. Right now, we'll build a classifier with 50 trees. Again, why 50? I like 50. There's no other reason. Again, for your final model, you have to try everything and pick the one that works best. But right now, let's just do 50. Once you have the classifier, you can call the train method on that, which will train that classifier. So you need to give some training features. We have to say, what are our training features? This is our training features. You have to show two things. What are the inputs and what is the output? Where should I learn from and what should I predict? So class property is what should we predict? So we said, predict whatever is contained in the land cover properties and learn from the input property. So rest, everything is your input to the model. So there has to be V1, V2, and so on, right? All the way through V12. There's an easier way to create this list. Since we had sampled it from a composite image, we can just use composite.bandnames. Because since we sampled it from there, the properties are the names of the bands of the composite. So we can use that. And we can skip the rest of the parameters. Done. So we have a trained classifier. At this point, the classifier has been trained and is ready to predict. What it needs is, give me 12 values. I'll tell you what the class is. That's what the classifier is ready. And we can say, now go and look at every other pixel. There are so many unlabeled pixels. Look at each pixel. There are 12 values there. Go and classify them. So let's classify this. We can say, take our composite image and say dot classify. Classify with the classifier. Done. We have classified the image. Let's take a look at the result. To look at the result, we need some Wiz params. We have the output will be either of the 4 class values. We have class from 0, 1, 2, and 3, right? So the output will be an image where each pixel is either 0, 1, 2, or 3, depending on the predicted class. So we'll 0, max 1, and we'll assign a palette. So we're going to use this palette, and let's just add that to the map. Let's say add a classified image, Wiz params. Right. Oops, I think, I did max 1. I should be max 3. So, and I should also clip my image. So now the classifier will run and we'll see the visualize results streaming in tile by tile. And you can see the process completing tile by tile. And you can see the tiles coming in. And you can see we have our final output. Let's turn off this and let's zoom into some region. And you can see the results of our classification just by having around 40 points, spending about maybe 15-20 minutes labeling some data. You are able to achieve this classification, which is pretty good. I think at the first glance, it looks pretty good, where you have the water, bear, urban, and vegetation class labeled. We can go one step further and say our goal was to extract water. So we'll just say water is classified equals to 2. That was the class that we had assigned to it. And we can just visualize the water here. And if your goal was to do water detection, this is yet another technique where you can build a machine learning model, do a supervised classification using the training data that you created or you received from somewhere else. And that would be another method to detect water. There's a question on the band properties. So let's say print classified, sorry, print, we have the composite here. So we have the composite here, and this is a helper function that gives you the band names. So you have this image having these bands. If you just want to get a list of all the bands here, this function will give you a list of those bands. And since this function requires the input properties, which will be the same as the band names, because when you sample an image, the resulting properties that are assigned by the sample region function is based on the band names. And that's why we are able to use here. No, okay, so this is actually the pixel value, because the Sentinel-2 image bands represent reflectance. But as we learned earlier, Sentinel-2 bands, when we get the data, they are multiplied by 10,000. So they can store them as integers. To get the reflectance of that pixel, you multiply by 0.0001. And that's your scale factor. So this is actually the reflectance of the pixel. The reflectance of the pixel will be between 0 and 1. So one of the pre-processing things that we can do is we'll teach you much better way to do this, but we can multiply it by the scale factor. And now when you do this, your training features will actually be the reflectance values. So it's not a count of pixels, it's a single point, right? So it's a single point, and at that point, we'll extract the reflectance values from all the 12 bands. And this will be the reflectance. Right, so now it's much more clearer. We'll learn to do this properly in the subsequent scripts. Yeah, so the question is, for crop classification, should we first mask out non-crop areas and then classify crop areas? Yes, that's the best practice. That's the way to do it. So the idea here is you have to, if you're trying to classify crops and you have training data for, say, wheat and maize, right, that's your training data. If you try to say wheat, maize, and other, the other class has so many other classes, right? Your classifier will not be able to learn that correctly. So if you say, I have some other ready-to-use data sets, which will tell me which are the crop areas, which are non-crop areas. And we'll learn this a little later on in the script, where we'll show you how to actually do a crop mask. So the script 5C exercise is actually showing you how to do this. So you extract that and say, I'm doing crop classification. I'm only interested in pixels that are crops. So you remove everything else and say, within this cropland, I will now do classification of wheat versus maize. And that your classifier will be able to learn much better. So you drop training points only on those regions, you classify only those regions. For water, let's say you want to classify water into open water and water with algae. Then you first take GRC or some other data, do a water mask, and then train your classifier to only work on water pixels and then classify them further. So again, this is more like a hierarchical classification. You try to remove pixels which are not relevant to your classification and then train a model to detect whatever is remaining. Okay, so we finished building our script. We did the classification for our chosen city. Now we'll work on exercise 1C, where you have to pick a region that you want to classify and perform the same 4-class classification by collecting your own training data. Vigna, can you explain the exercise?